All right. So just to kind of review this, these last couple ones, because I know I didn't go through all of it. You do talk about the slope and the line and everything, but I think it was more these last two questions I kind of wanted to go over because I rushed through them. Based on the slope of the measurement, what can you conclude? So when we're doing the parallelogram and we measure the slope, oops, give me a second here. This one. So if we look here, if they have the same slope, then they must be parallel to each other. So that's what we can conclude. So even if you guys do like rough language, this is math. I'm not going to grade you for your sentence structure too much, just as long as it makes sense. So if you're just like, if you start a sentence with because, I'm like, well, I don't care. It's not an English class, but it has to be it has to make sense because the slopes are the same. That means that the lines are parallel. It can be something that's simple. I know usually they say they go like opposite sides of the quadrilateral have equal slopes, which means that the opposite sides are parallel. Therefore, the definition of the quadrilateral is a parallelogram. Put it in your own words. Like that's way too complicated. Just because the slopes are the same, that means the lines are parallel. Um, because the slope, that means I guess I'll call them opposite sides. Can be a little more specific, I guess, but you don't have to be this complicated. Suppose you repeated steps 5 and 6 with different line segments left. So if we did 5 and 6, so measuring the diagonals, what did we do here? Oh, yeah. So we created them. That's when we created the parallelogram. They so this they should still create. Ooh, I can't spell today. I'm sorry, guys. Create a parallelogram because because we already proved it. We proved that the diagonals of a parallelogram cross each other or bisect each other. So this, even here, I did a little too complicated of language. Um, but it's basically the lines cross each other at the midpoint. So that's why I'm saying bisect. So it's specific on what I'm talking about. The term diagonals just means the lines crossing it. So you can even say things like from the lines going from corner to corner, cut each other in half, something like that. And all I'm really saying is like, yeah, they still make a parallelogram, you know. So I'm right here. I'm just saying that we're proving that does a parallelogram. So just in your own words, make sure it makes sense though. Don't just put random words in there that you don't know. You're like, I think this is what the teachers would want. So here we're just saying that they're parallel. We proved it already. But now they're going to go into detail. What are we proving now? So we're going to prove that diagonals bisect each other. So I think I kind of went over this already. I thought we did this. I must have just explained it. But basically, what they're doing is, oh, that's terrible. It opens another one. So they take this parallelogram. So we have a parallelogram. we're going to already say that they're parallel. So remember how I said these little arrows mean that they're parallel? This double arrow means that the two double arrow ones are parallel. And these single arrows mean that these two ones are parallel. So we're saying that they're already parallel. And that's by definition of a parallelogram. So they're just specifying which sides are parallel. Here, draw line segments. So they're just saying we're going to draw this diagonals, the ones that cross each other. And then after that, we're going to make a point E, point right in the center. And then we're going to say that this angle is equal to this angle because of alternate interior angles. So this angle equals this angle, this double one equals this double one. And then from there, so we said that alternate interior angle theorem, because again, just imagine these as lines being extended by a lot. So give me a second. So I have these. Oh, is it off again? No. Oh my gosh. I don't know why Admentum hates my pen. Oh wow, this is really bad. All right. Well, just imagine that if you continue this line and continue this line, you would have these alternate interior angles. So that's all it's saying is alternate interior angles. Or you can think of it as this line increasing and this line increasing for these two angles. I just wish I could draw it. Maybe I can draw it on this page. Okay, this page looks fine. So if I pretend that this line, oh my gosh. So there's my quadrilateral and the intercepts. So this line right here is alternate interior to this line over here, except my drawing's terrible. But you guys get the idea. And then if we have another diagonal, the same thing's going to go for these other angles. All right. So that being said, now we can say that we'll have that angle side angle. So I think I did this last time. If you guys want to see it again, you guys can check out that video. But it was basically this idea that this angle, this, and then this angle and this. And we know that this one is parallel or equal to this one. So we have angle side angle. This is just them doing it all formal, and they have steps that I wouldn't include because it's very specific. All right, so now let's get started. So now we want to prove that if two lines bisect each other, they'll make a quadrilateral. So first, we have to identify that there's a bisector. So let's take a look at this diagram. Okay, so we haven't made that yet. So that's another thing you guys can do is just look at the diagram to see where they're at. So we're trying to prove that's a quadrilateral. So I always start with the end in mind. I know this is what I'm proving. What am I given? These two bisect each other. Okay, so I know that we start off with these two bisecting each other. So now the definition of bisection is that it cuts it in half. So it makes a midpoint. So that's going to be this right here. Make that midpoint. Next, the vertical angle theorem. So vertical angle theorem. Oh, that's this theorem right here, where this angle is equal to this angle. So if we call this AC and I call this one BD and this is E, then I'm saying that angle AEB is congruent to angle DEC. And I can see that over here. Except they're doing it for both. They're also doing it for this one. All right, and the next one, it says, so this satisfies the side angle side criteria. And that does, because this is the midpoint. This is congruent to that. And then we said that this and this are congruent. So I have a side, angle, side, side, angle, side. So now that I'm saying that those are congruent, then if I made a line connecting these would also have to be congruent. So corresponding angles with corresponding sides. Oh, I forgot to create the actual parallelogram. So this would have to equal this, what they're saying. I thought they were going to do by side, 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 and then prove it later, but they're like, nope, going to go straight into this. Because these angles are congruent, that means they have to be parallel to each other. Meaning that the whole thing is a parallelogram. So that's just how geometry is. It's more about putting everything step by step as we construct it, as we're proving it. I've always made the analogy, it's like in English where you have to write a paragraph and you have to state your concrete detail and your evidence. So it's the same idea. By the definition of a rectangle 90 degrees, but those theorems were applied to general properties of parallelograms, not just rectangles, recognizing the adjacent sides are perpendicular. So this is just saying that rectangles are parallelograms too, because the opposite angles are congruent, opposite angles are congruent, opposite sides are parallel. So now we're going to apply it to a rectangle. We're going to prove that they're rectangles. So if I open up my rectangles activity, so I have this rectangles activity, and I'm just going to measure the distances. So I go here, 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 and I already know what the angles are. So in this case, when I'm doing this, oh, and it wants me to make the diagonals. I guess I haven't made the diagonals yet. Boom, 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 boom. You have to label a point here in the middle, otherwise it's not going to let you find the length. So more specifically, it looks like for rectangles, they're all congruent. This might be the one that I had it confused with last time. What am I measuring? Oh, I'm measuring the entire diagonal, the length of the diagonals. So AC is 7.21. Okay, so in a rectangle, our diagonals are congruent. So just to prove it, I'm going to export my image. Save it as rectangles. That's fine. I think I put it on my desktop. So if I go here, can I do this? I forgot if I can do that or not. Apparently not. Insert image. File. Nope. Not in downloads. Where's the rectangle? There it is. What's nice about using the default name is it saves the actual activity and everything for you. So that, and then it makes it easier for me to type this in also, because I can barely read it there, but I can read it. We got those. How do the measurements of diagonals compare? In the rectangle, the diagonals are equal. Move the vertices around to notice the difference. So let's move the vertices of this rectangle around and see if anything changes. So the diagonals look like they remain congruent no matter what I do. I'll try to make it taller. Oh, this one changes it diagonally. That's interesting. This will make it go up and up. Nope, changes it. That just changes the side. I wanted one that would make it go up and down. This one goes left and right. This one just makes it bigger or smaller. Okay. But either way, no matter what I'm doing, it remains, they remain congruent. When I change the size, diagonals remain, you can put stayed congruent, remain congruent. So explain how you prove in your observations, traditional proof. So the way we would do this with a traditional proof, I would say, is if I made this, if I created the diagonal, so I would create the diagonal. Oh, that's why it sounded like I proved it. If I made the diagonal, I have two congruent triangles, right? So if I have two congruent triangles, I'm like, okay, so actually, hold on. I'm like thinking way too hard. Let's picture this as two rectangles. And I keep forgetting I shouldn't draw on the new ones because for some reason it hates it. So here's one rectangle, here's another rectangle. They're congruent. So that means these have to, oops. So this side is congruent and that, and then I have a right angle, so they're a right angle. So basically, these are congruent by side, angle, side. So I can do something easy by just saying that, like, oh, there we go. I don't know why I was acting all weird. When I make the diagonals, I created 4 triangles. I'm going to say 4. I created triangles that are congruent by side, angle, side. This means that all corresponding means that if we moved it to the other triangle, it corresponds with it. It stays the same. Corresponding parts are congruent. And that's what's important about proving that triangles are congruent, because if you can prove that the triangles are congruent, anything inside that triangle is going to be congruent to another part. So corresponding parts are congruent. So the diagonals must be congruent. Then just evaluate how you're doing. So hopefully you're starting to do better with these proofs. You're starting to understand them a little bit more. If you're still having trouble, write that down as well. Like I said, I don't want you guys to take the self evaluation lightly. It's not necessarily for the teachers to know how you're doing. It's for you to ask yourself, am I understanding this the way I think it is? And then explain what you do understand from it and stuff like that. It gives you time to reflect if you're understanding it correctly. If you find yourself not knowing certain things, you might want to like consider reviewing it or watching these videos again if you're watching online right now. What are observed in the lesson activities written? So that what's observed is our diagonals are congruent for rectangles. They're not congruent for parallelograms, as I thought mistakenly in the other one. I deal more with rectangles, so I just assumed it was the truth for parallelograms, but it makes sense. One of them has to be larger than the other. If we think about it, like after I thought about it, I'm like, oh, that was a stupid thing to think, because if I look at it, obviously this one is shorter because it's really close than this one because they're further away. All right, so we're gonna, again, I like starting knowing where I'm gonna end. What am I proving? I'm proving that the diagonals are congruent. So if I'm proving that AC is congruent to BD, that's where I'm ending. All right, so let's work from the front to the bottom. The quadratic, and for these, it also makes it easier because then it's like you eliminated one of the choices. When you guys are doing this, make sure you're reading and understanding the reasonings why. Don't just like, oh, it doesn't fit there, it doesn't fit there. Take a minute to understand it. So quadratic, so first we have to say that's a rectangle. So this is a rectangle. What do we know about rectangles? Well, rectangles are parallelograms. It's part of the definition of a rectangle. It has to be a parallelogram with 90-degree angles. All right, so from there, let's see what we can do here. AC is parallel to BD. So let's take a look at this one. So according to this, the opposite sides have to be congruent, and it's saying that this angle is equal to this angle. Well, that's true because it's a rectangle. Oh, wait, but it says opposite sides of a parallelogram are congruent. So opposite sides of a parallelogram are congruent. So we're not talking about angles, we're talking about the sides. From there, we can say that these angles are congruent because they're rectangles. Obviously, if all the angles in a rectangle are 90 degrees, then these two angles have to be the same. And then from there, we're going to do this, and then we do what I said. Corresponding sides of congruent triangles are congruent. That's the same thing as what I said. Corresponding parts of congruent triangles are congruent. I say parts because I think of angles. Angles are congruent on congruent triangles too. All right, and our summary. So what is a parallelogram? A parallelogram is when two sides, not ides. What happened there, Edmentum? Come on, you're better than this. So, and these theorems all apply to parallelograms. So if a quadrilateral is a parallelogram, then its opposite sides are congruent. If a quadrilateral is a parallelogram, then the opposite angles are congruent. So opposite sides, opposite angles in a parallelogram. If a quadrilateral is a parallelogram, then the diagonals bisect each other. So that one is a little more nuanced. This idea that they cut each other right at the midpoint. And then this one, if the diagonals of the quadrilateral bisect each other. So if we have a four-sided figure, any four-sided figure, and these two bisect each other, then we know it has to be a parallelogram. And I'm marking that the sides are congruent and the sides are parallel. All right, and then for a rectangle, what's special about it is not only do they bisect, not only do the angles bisect each other, but they're all equal to each other. So this is why I'm only using one mark instead of two. All right, so those are the main theorems that we're going to use for this mastery test. If you guys haven't answered the question, feel free to do so. I know this was a short class, but I'm here if you guys have questions about anything. So give me a second. Let me stop the recording. That is not how I stop the recording.